This is section 7.6 and 7.7 of Honors Algebra 2, Quadratic Functions. So a quadratic function is a function that can be written in either one of these two forms. The general form, where we've got ax squared plus bx plus c is our function, where a is not equal to 0, because if a was 0, we would lose the highest power of the variable being 2, and we'd all of a sudden have a linear function. Or vertex form, where a times x minus h quantity squared plus k is our function, and again where a is not equal to 0, or all of a sudden it's no longer quadratic. When it's in vertex form, we can easily pick out the vertex. That's the name vertex form, and the vertex is h comma k. The graph of a quadratic function is always a parabola, and we saw that with quadratic equations. So quadratic functions are just functions formed from quadratic equations, and to graph them, all we really have to do is replace f of x with y, and we can graph it just like we graphed quadratic equations. Here's some examples. We're going to find the vertex, the domain, the range, and the zeros, which remember are the same as the roots of the function, and we're going to graph it. So f of x equals 2 times x minus 3 quantity squared plus 1. So let's graph y equals 2 times x minus 3 squared plus 1. To do that, we're going to pick out the vertex first. The vertex is h comma k. H is the number subtracted off from x, so that is 3, positive 3. Even though it's x minus 3, h is positive 3. It's the opposite sign. K, though, takes the same sign as the number on the right-hand side. So the vertex is 3 comma 1. We'll start with that. That means the axis of symmetry is the vertical line that goes through the vertex. And I won't draw it this time because we don't need to draw it. It's not part of our graph. Let's plot a few other points. If x is 4, because that's 1 to the right of the vertex, then we'll have 4 minus 3 is 1, 1 squared is 1, 1 times 2 is 2, plus 1 is 3. So when x is 4, y is 3. We'll label that point. Because of the symmetry, I know that if I go 1 to the left of the vertex, when x is 2, I would have the same y value of 3. So 2 comma 3. Alright, let's pick one more point. When I go 2 to the right of the vertex, when x is 5, I've got 5 minus 3, that's 2, 2 squared is 4, 4 times 2 is 8, plus 1 is 9. So I've got the point 5, 9. And I know that if I go 2 to the left of the vertex, so if I go to 1, I will also be at 9. Okay, so now I can sketch my parabola. Alright, so I found the vertex. That's 3, 1. I need the domain, the range, and the zeros. Okay, the domain for any quadratic function is going to be all real numbers, because there is no restriction on what I can plug in for x. Any number, any real number that I plug in for x, I will get out a number for y. The range, though, is not all real numbers, because there are numbers for y that I will not ever get no matter what I plug in for x. And I can see that from the graph, because anything below my parabola, anything down here, for example, on the y-axis, I'm never going to get. Those are y values I will never get. My graph has no points below the vertex. So the range is determined by the vertex. In this case, it's everything from the vertex and above. So the range here is the set of all y, because range is y, such that y is greater than or equal to 1. Why 1? Because that's the y coordinate of the vertex. That's the lowest value for y I can get out when I plug in numbers for x. And I can get that, so I want it greater than or equal to 1. I can get anything above 1, I just can't get anything below it. The zeros are the values we get when the function is equal to 0. Now the function is the same as y, so if y is equal to 0, what numbers do I get for x? Well, my graph tells me that I don't get anything. When y is equal to 0, there's nothing that will give me 0 when I plug it in for x, because there's no x-intercepts. So the zeros are the x-intercepts. So if I have the graph, I can find the zeros by looking at the graph. Here, there are none. Now, if I were to set this equation equal to 0 and solve it, I would get two imaginary solutions. So this equation has solutions when y equals 0. They're just imaginary. There are no x-intercepts, though, for my graph, so there are no zeros, because the x-intercepts have to be real numbers. They can't be imaginary numbers. Number 2. f of x equals 3x squared minus 6x plus 1. Okay, this time we are in the general form, and so the vertex is not as easy to pick out. However, I can get it if I can rewrite my equation in vertex form. To rewrite it in vertex form, I'm going to complete the square. So let's start with y equals 3x squared minus 6x plus 1. And let's complete the square. So let's subtract the 1 to the other side. And we need to deal with that 3. Instead of dividing everything by 3, I'm going to factor it out on the right-hand side. Because if I divide by 3, I'll have y minus 1 all over 3, and that's a mess. So instead, I'm going to factor it out. And I'll leave a space because I'm going to end up adding a number in there. So I'm going to complete the square on what's in parentheses. So I take the middle number, negative 2, I divide it by 2, it gives me negative 1, and I square it, that gives me positive 1. So I'm going to add 1. Now, I added a 1 inside the parentheses. But what did I really add to the right-hand side of the equation? I really added 3 times 1. I really added a 3 to the right-hand side, because that 1 inside the parentheses is really a 3 outside of the parentheses, because it gets multiplied by the 3. So to keep my equation balanced, I have to add a 3 to the left-hand side. I added a 1 inside the parentheses on the right, which is really adding a 3 to the right-hand side, so I add a 3 to the left-hand side. So that will give me y plus 2 equals 3 times, and now this factors as x minus 1 quantity squared. Or y equals 3 times x minus 1 quantity squared minus 2. And now I can pick out the vertex. The vertex from here is easy to pick out. It's 1, negative 2. So 1, negative 2. And if x is 2, I'll have 2 minus 1 is 1, 1 squared is 1, 1 times 3 is 3, 3 minus 2 is 1. So when x is 2, I get 1. By symmetry, I know when x is 0, I will also get 1. Let me label these points so far. Okay. And I can sketch my parabola. Now, what's the domain? The domain for any parabola, for any quadratic function, is all real numbers. What's the range? The range is limited by where the vertex is. So the range here is the set of all y such that y is greater than or equal to negative 2. That's the lowest y value we can have, and we can have anything above it. What are the zeros? Well, there are 2 of them here, because there are 2 x-intercepts. There's 2 places where my graph crosses the x-axis. But those are not going to be whole numbers. One of them is between 1 and 2, and the other one's between 0 and 1. So in order to find them, I need to actually solve my equation. So if I take my equation, 0 equals 3x squared minus 6x plus 1, and I solve this, then I will have the zeros. Alright? Why don't we use the quadratic formula? So x equals negative b, that's 6, plus or minus the square root of b squared, so that's 36, minus 4 times 3 times 1, all over 2 times 3, which is 6. So x equals 6 plus or minus the square root of 36 minus 12 over 6. So x equals 6 plus or minus the square root of 24 all over 6. Square root of 24 is the square root of 4 times the square root of 6, so that's 2 square root of 6 all over 6. Cancel the 2 out of everything, gives me 3 plus or minus square root of 6 over 3. Those are zeros for my function, because those are the x-intercepts. 3 plus square root of 6 over 3, and 3 minus square root of 6 over 3. So when you have a function in general form, you don't have to complete the square if you realize that the x-coordinate of the vertex is always going to follow this format. The x-coordinate of the vertex is always going to be negative b over 2a. So in the previous example, in order to find the vertex, I had to complete the square and put it in vertex form. But if I had taken negative b over 2a, I would have negative of negative 6, that's positive 6, over 2 times 3, which is 6, so I would get 1. And that was the x-coordinate of my vertex. So that formula comes from completing the square on a general quadratic function with letters instead of numbers. We won't bother deriving that here. But just know that you can find the vertex from the general form by taking negative b over 2a. That will give you the x-coordinate. To find the y-coordinate, you plug that in for x and solve for y. So, for example, number 3, g of x equals 6 plus 6x minus 3x squared. Let's rewrite it with a y and with things in the proper order on the right-hand side. Negative 3x squared plus 6x plus 6. So the x-coordinate of the vertex is going to be negative b over 2a. Now that I'm in the proper form, I can pick out b and a. b is 6, so that's negative 6 over 2 times negative 3, because a is negative 3. So I get negative 6 over negative 6, which is positive 1. So the x-coordinate of my vertex is 1. To find the y-coordinate, I plug in 1 for x and solve for y. So y would be negative 3 times 1 squared plus 6 times 1 plus 6. So y is 1 squared is 1 times negative 3 is negative 3 plus 6 times 1 is 6 plus 6. So y is negative 3 plus 6 is 3 plus 6 is 9. So my vertex is the point 1, 9. I can graph that, 1, 9. This time I know my parabola is going to go down. How do I know it's going to go down? Because a is negative. So my parabola is going to open down. So I can still find other points on it. If x is 2, then I plug 2 into my original equation, and I'll have y equals negative 3 times 2 squared plus 6 times 2 plus 6. So if I work that out, 2 squared is 4. 4 times negative 3 is negative 12. 6 times 2 is positive 12. So that becomes negative 12 plus 12, and that's 0 plus 6, and I get 6. So when x is 2, y is 6. By symmetry, when x is 0, y is also 6. Okay, and I can sketch my parabola. Actually, it should go all the way down. There we go. Alright. What is the domain? Domain is all real numbers. What is the range? The range is a set of all y's such that y is less than or equal to 9. Not greater than or equal to anymore, but less than or equal to, because this time a parabola goes down. Alright, what about the zeros? Well, that's solve for them. So 0 equals negative 3x squared plus 6x plus 6. And notice I can divide everything by a negative 3. And so 0 will equal x squared minus 2x minus 2. And that makes it easier to solve. I'll still do it by the quadratic formula. So x equals negative b, that's 2, plus or minus the square root b squared, which is 4 minus 4 times 1 times negative 2, all over 2 times 1. So x equals 2 plus or minus the square root of 4 plus 8, which is 12, over 2. Square root of 12 is the square root of 4 times the square root of 3, which is 2 radical 3. So this gives me 2 plus or minus 2 radical 3 over 2. The 2's will all cancel. I get 1 plus or minus radical 3. So those are my zeros. 1 plus radical 3 and 1 minus radical 3. Those are the 2 points where my graph crosses the x-axis. The 1 plus radical 3 is going to be the one on the right, because that's a positive number. 1 minus radical 3 is going to be the one on the left, because that's the negative number. Notice that if a is negative, if a is less than 0, then the parabola opens down, just like that one did, and the function has a maximum value. It has a highest value. That maximum value is 9. The function will go no higher than 9, because that's where the vertex is. If a is positive, then the parabola opens up, and the function has a minimum value, the bottom value. And that is the y-coordinate of the vertex at the bottom. So this maximum or minimum value is the y-coordinate of the vertex. Now let's say we have this quadratic equation, 2x squared minus 6x minus 8 equals 0. How do we solve it? Okay, well, we can factor out a 2 and get x squared minus 3x minus 4. And we can factor x squared minus 3x minus 4. It conveniently factors as x plus 1 times x minus 4. So then to solve it, we set these parts equal to 0. 2 doesn't give us anything, but if x plus 1 equals 0, then x equals negative 1. Or if x minus 4 equals 0, then x equals 4. So our solutions are negative 1, 4. Those are the roots of this equation, which if we were to graph them, since these are real numbers, would be the zeros of the graph. But let's say we're going backwards, and we have the roots, and we want to write the equation. So let's say we are told the roots are negative 1 and 4. How can we write the equation? Well, we can do so by starting from that step, except we won't know the 2. The 2 didn't play a role in what the roots were. If the roots are negative 1 and 4, we know that x plus 1 must be a factor of the equation, so that negative 1 is a root, and x minus 4 must be a factor of the equation, so that positive 4 is a root. So we at least know that. And that equation would have those roots of negative 1 and 4. But so would any equation with those and any constant a in the front. So a could be 2, which would give me the equation I have on the left. A could be 3, which would give me a completely different equation, but that equation would also have roots of negative 1 and 4. If I'm multiplying every term of the equation by the same constant number, then that does not affect the roots, because I could just divide every term by that constant number, and the other side is 0, and 0 divided by that number is 0. So that constant doesn't affect what the roots are. So we can find the equation if we have the roots. Alright? Let's generalize that down here. If R1 and R2 are roots of a quadratic equation, then x minus R1 times x minus R2 must equal 0. So that R1 comes from x minus R1 equaling 0, and R2 as a root comes from x minus R2 equaling 0. So we take each of the roots, we form a factor out of each one by taking x minus that number, and those are factors of a quadratic equation that has r1 and r2 as the roots. If we FOIL that out and we combine like terms, we would end up with x squared minus, and then in parentheses, r1 plus r2, close the parentheses, times x, plus r1 times r2 equals 0. So if we were to FOIL out the equation I have on the top there, and then combine like terms and factor out an x from the two terms that have an x, that's the equation I would get. So if r1 and r2 are roots of a quadratic equation, then I know this is an equation that has those roots. Thus, notice the coefficient of the middle term, that middle number, is the sum of the roots. And that last number is the product of the roots. So it turns out that x squared minus the sum of the roots times x plus the product of the roots equals 0 will be an equation that has r1 and r2 as roots. But there are actually an infinite number of equations that have that, because I could take this, I could multiply the whole thing by any real number constant a. So that makes it really easy to then find the equation if I know the roots. I add them together, that becomes the number in front of x. I multiply them together, that becomes the number on the end. So let's see that in action. Let's find a quadratic equation with roots 2 plus I over 3 and 2 minus I over 3. Those are complex numbers. They're complex roots. But it will give me a quadratic equation with real numbers. So what is the sum? The sum is we add 2 plus I over 3 plus 2 minus I over 3. These are fractions. They have a common denominator of 3 already, so if we add them together, we add the numerators. 2 plus 2 is 4. I minus I is 0. So we got 4 over 3. The sum is 4 over 3. What's the product? Product we multiply. 2 plus I over 3 times 2 minus I over 3. Alright? We FOIL out the top. 2 times 2 is 4. Then we've got minus 2i plus 2i, so those cancel. And then we've got I times negative I, which is negative I squared. But I squared is negative 1. This is negative of negative 1, which is positive 1. And then I've got 3 times 3 on the bottom, which is 9. So 5 over 9. So that means an equation that has these two roots would be x squared minus 4/3 x plus 5 over 9 equals 0. That's the conclusion I just reached above. If I take the sum of the roots and take the negative of that in the middle, and I take the product of the roots and add that onto the end, then that will be an equation that has those roots. Now there are other ones. All I have to do is multiply the whole equation by another number. I can also clear the fractions if I don't like the fractions. I can multiply everything by the common denominator of 9 and get 9x squared minus 12x plus 5 equals 0. That would be a quadratic equation that has those roots. And again, I could multiply everything by, say, 2, and I have another quadratic equation that also has those same roots. But this is a quadratic equation, and that's all I'm asked for, is find a quadratic equation with those roots. Last problem. Find a quadratic function f of x equals ax squared plus bx plus c such that the maximum value of f is 8 and the graph of f has x-intercepts of 3 and 7. This time I'm writing a function instead of an equation, but it's almost entirely the same thing. If the x-intercepts are 3 and 7, then those are the zeros of my equation, and the zeros of my equation become the roots of my equation. So really this is telling me that r1 is 3 and r2 is 7. Okay, so the sum is 3 plus 7, which is 10, and the product is 3 times 7, which is 21. So I at least know that my function looks like this. F of x equals a times x squared minus the sum, which is 10, plus the product, which is 21. Now I have to put that a there because I still need to account for the fact that the maximum value of f is 8. I haven't used that yet, so I need to find the specific quadratic function that has a maximum value of 8. Now if it's a maximum value, then my parabola must open down so that it has a maximum at the top where the vertex is. If it opens down, that means a is going to be negative. A has to be less than 0 in order to force it to be down. So I know that. Okay, but now I need to find what the actual value for a is. Now if the maximum value is 8, that means the y-coordinate of the vertex is 8. Because that's where the maximum is. Okay? I need to find the x-coordinate of the vertex. Well, because of symmetry, the axis of symmetry lies exactly halfway between 2 points that are on the same level. Well, my x-intercepts are on the same level. So the axis of symmetry will lie halfway between those two x-intercepts. So if I take the average of those two, 3 plus 7 over 2, which would be 10 over 2, or 5, then I know the axis of symmetry is 5. And the axis of symmetry is the vertical line that goes through the vertex. So it has the same x value as the vertex. Thus, the vertex must be 5, 8. And so if the vertex is 5, 8, I can plug that into my equation and solve for a. So I'll have 8 equals a times 5 squared, which is 25. That should be an x, negative 10x, minus 50, 10 times 5, plus 21. So 8 equals a times 25 minus 50 is negative 25, plus 21 is negative 4. And thus, when I divide both sides by negative 4, a equals negative 2. So that's the way I can find a, is use the vertex as a point on the graph. Plug in 8 for the function, which is y, and plug in 5 for x. So my final answer, my final function, is f of x equals negative 2 times, parentheses, x squared minus 10x plus 21. That is the specific quadratic function that has roots of 3 and 7, but has a maximum value at 8. And notice a ended up being negative, as I said it needed to be. We'll do more examples of that in class. Here are your immediate practice problems. Graph the function, state its vertex, domain, range, and zeros, just like our earlier examples, and then find a quadratic equation with roots 3 plus I over 2 and 3 minus I over 2. That should be just like example number 4. That's the end of section 7.6 and 7.7.